Okay, so we're in the chapter 3 now, and um, the official title of chapter 3 is something different than this, but essentially this is what it's about. What we're going to be looking at is developing more conversion factor skills and looking at more chemically relevant problems. So what I'm going to title this section of videos is Conversion Factors in Chemistry. And we're going to start with a concept of a mole, all right? Something you may have heard about, but just a quick little review. Atoms are really small. I mean, they are tiny. We talk about looking at one atom and measuring things in terms of AMU. So, looking at a mass and getting a mass in terms of atomic mass unit. An AMU is about 10 to the minus 27 kilograms. So that is very, very small. So it's really hard for us to actually measure individual atoms, even individual molecules. It's hard to see their mass. It's hard to even pick them out from a grouping of atoms and molecules. So what we have to do is we have to set a standard. And we're going to do this math in the background that allows us to bring things up from things that are small and make them bigger. And what allows us to do that, all right, is what's known as Avogadro's number. Essentially, because atoms are so small, it takes a lot of them to get to a situation where we can measure them in terms of their mass, when we can notice them even physically, just living in this world. Okay, they're just so small that you actually need a great number of them to notice. Okay, be able to measure. Avogadro's number allows us to look at large numbers of objects. And in fact, Avogadro's number is something that you want to memorize. It's 6.022 times 10 to the 23rd objects is equal to 1 mole. Okay? So this mole is like a grouping of objects. It stands in place of a number. Just like a dozen stands in for 12, mole stands in for 6.022 times 10 to the 23rd, right? 1 mole of water is about a tablespoon. So now we're in a situation where if we get that many objects, it's something we can notice, it's something that we can measure, it's something that's more easy for us to manage because we ourselves are a lot bigger than atoms, right? Avogadro's number also allows us to count by mass because in setting a standard, what we can do is we can look at something like atomic mass. So in the periodic table, we know that we have a number without a decimal place, that is the Z, the atomic number, and that's the number of protons. And I just picked boron again, all right, just as an example. We know that a single boron atom, if you just look at one atom of boron, we know that its mass would be 10.81 AMU, right? We learned that in previous chapters. To make this more manageable, though, and even though this is math that happens in the background, you just kind of have to take my word for it. This 10.81, it also describes what was going to be known as molar mass. This same number, right, on the periodic table, it tells us that if we have a 1 mole of boron, that's equal to 10.81 grams of boron. So it's numerically equivalent. And like I said, there's this stuff happening in the background that we just don't have time to get into, but it tells us, okay, if I could count 6.022 times 10 to the 23rd B's, what you get out is 10.81 grams. Now, this is something we can measure. We have balances that can look at this number, where 10.81 AMUs is impossible to make a balance so small, so delicate, so intricate, where we could actually get that measurement down, all right? We call this value molar mass. So I want to go over it one more time. When you're talking about one object, the units are AMU, because you're talking about something that's small. We could also talk about this grouping of objects that we call a mole. And then that brings the numbers up into something that's measurable, something that's workable, right? Molar mass. So on the periodic table, you don't just see that number with a decimal point now for an element as an atomic mass, it's also a molar mass. And if you look at how I wrote that molar mass down, I wrote it like an equality. And we know that equalities are conversion factors. So we can take that equality and we could write it as 10.81 grams per mole. 10.81 grams of B for every mole of B. This allows us to take mass information and make it mole information, or to take mole information and make mass information. It allows us to count by mass. Because remember, if I know Avogadro's number, I know how many objects there actually are in a mole. All right. Take, for instance, something like we're going to use lead in an example. And underneath lead on the periodic table, we have 207.2. So in problems now, we have to look at that number with a decimal point and say, all right, if I'm talking about one lead atom, this is 207.2 AMU. But if I'm talking about a grouping of lead atoms, lead has a molar mass that's 207.2 grams of lead per every mole of lead. That number with a decimal point on the periodic table has units of AMU or grams per mole, right? So let's do an example that kind of illustrates how we can count by mass, right? A 5.00, let's just do 00 gram sample of lead, right, contains how many atoms of lead, right? So we now, based off the information provided, right, have a method that takes mass and counts atoms, all right, by linking together molar mass and Avogadro's number. Again, it's a series of tools we have to develop, series of skills we have to look at and be able to utilize in problems like this, all right? Now, we approach this conversion factor problem just like we were approaching conversion factor problems in the beginning part of the course. What are we asked to analyze? We're asked to analyze 5.0000 grams of lead. Notice, I'm not only writing the unit down, I'm writing the identity, right? We take our 5 grams of lead and we have to turn that into atoms of lead. Now, the only way that we can count atoms, because they're so small, is with Avogadro's number. So I know somewhere I'm going to have to use Avogadro's number. So it kind of makes sense. If I can use the molar mass of lead to get moles, then I can make moles into atoms via Avogadro's number, and then I've essentially finished this problem, okay? So here's the thought process. On the periodic table, I know I have this conversion factor that exists now, and 207.2 grams of lead is equal to 1 mole of lead, right? My units of grams of lead will cancel and I'll be left with mole of lead. Do I know a relationship between moles and atoms? And the answer is yes. After today's video, you guys will know that if I ever want to count anything, 1 mole of anything, right? In this case, it's going to be 1 mole of lead, is 6.022 times 10 to the 23rd, right? Atoms of lead, right? It's a grouping of that many atoms. And so I can plug this into my calculator and we can do math, but kind of hopefully you can kind of see the setup and the feel of the problem is familiar. What am I starting with? Where am I going? What do I know, right? In terms of mathematical objects, information from the periodic table, etc., that I can link together to get the information that I need. So I plug this in my calculator and I pay attention to significant figures. I'm doing multiplication. Over here, there's 1, 2, 3, 4, 5 significant figures. Molar masses, right? These are measured. We definitely need a measuring device to figure out what they are. So there's 4 significant figures here. Avogadro's number actually comes from a measurement. That's some of the math that's happening in the background, so you're just going to have to trust me on that. But Avogadro's number is subject to significant figures as well. So this has 5 significant figures, this has 4 significant figures, this has 4 significant figures. So my answer has 4 significant figures. And rounding to those significant figures, I get 1.453 times 10 to the 22nd atoms of lead. Is that a lot of atoms in a 5-gram sample? Well, yeah, but that makes sense because atoms are just so small that even if you have a smallish, like 5 grams isn't that bad. You can hold it in your hands. It's nothing that's super heavy. But look at how many atoms it contains. It contains a large amount of atoms. Okay. So molar mass is something that lets us link to moles. And then from there, Avogadro's number can actually have us count. okay? Now, this is just one type of problem. We have to be able to take these conversion factors and flip them as needed. Same thing with Avogadro's number, and you're going to do a lot of practice using molar mass as an Avogadro's number for simple calculations in Chem 101, all right? The next topic that kind of leads us towards looking at molar mass for compounds, right? Let's actually just go there right away. All right, so let's look at the molar mass for compounds now. So we can kind of extend this idea not just to individual not just to individual atoms in the periodic table, but we can actually use for compounds / molecules as well. All right, so for example, if I look at something like oxygen, O2, right? And I asked you, okay, a single O2 molecule, right, which we know is a covalent molecule. This single O2 molecule, if you look on the periodic table, underneath O, you see 16.00. So if I asked you how much mass is contained in that single O2 molecule, you would rightly say, okay, well, there must be two 16s, so there's 32.00 AMU for that single molecule. Well, what happens if I have a mole of O2? What is the molar mass of O2? It's that same number, 32.00, but now with units of grams per mole. We also make sure we include identity, right? So the molar mass of O2 is 32.00 grams of O2 for every mole of O2, okay? So notice now, all I have to do for molecules and compounds is look at that number on the periodic table, right? And think about the species that are present and add them all together, right? And then that becomes the molar mass for that new object. So now this will allow me to calculate and count information with respect to O2, not necessarily just O, right? To drive that point home, let's look at something like CO2, all right? So on the periodic table, C has a 12.01 under it, right? Underneath O on the periodic table, there's a 16.00. So if you look at something like CO2, what we could ask now are things like, okay, what's the molar mass? Whenever you're asked for molar mass, just remember, you're not talking about AMUs, you're talking about units of grams per mole. So how would you figure this out? Well, you have two carbons, and you have one oxygen. So essentially what you have to do is 2 times 12.01 plus 16.00. It's a real simple concept, but it's good to go over because it's important. If I plug all this in my calculator, what I get is 44.01. And now let's write correct units, grams of CO2 for every mole of CO2, right? That is the molar mass of CO2, and that belongs to CO2. And every time you look at CO2, it'll have this same molar mass, and it's a fraction, so we can use it in problems as a conversion factor, okay? The next tool that we have to develop past molar mass, right? Having gone through Avogadro's number, having gone through ideas associated with counting by mass, is we have to develop skills associated with mole to mole bridges. And really, like this lecture, this video, it accounts for many of the skills that we'll use in the next 3 chapters, right? It really is incredibly foundational, right? Avogadro's number, molar masses, mole to mole bridges, right? So what's a mole to mole bridge, right? Well, let's just take a look at, let's look at H2O just for something different, right? The idea behind a mole-to-mole bridge is it allows us to change identity, okay? It allows us to talk about, right, one object and relate it to another object, right? And the rule that we're going to use for mole-to-mole bridges is anything that you can say about the individual species, you can also say about moles of that species. And that's something I'm going to reinforce again and again and again. All right, so let's just kind of look at this H2O as an example, and you'll see what I mean, hopefully, okay? If I look at this H2O, okay, this tells us how many H's and O's there are. If I look at one H2O molecule, you should be able to look at this and say, okay, there are two H's, okay? If I look at this one H2O molecule, you should be able to look at it and say there's one oxygen. These are equalities, so they're actually conversion factors as well, all right? We can definitely say there's one H2O, or for every one H2O, there's one oxygen found inside it. One H2O has two H's. We also can see that inside here, when we're referring to water, two H's are the same as one oxygen, okay? I'm gonna put quotes around the oxygen so you don't think it's a 10. So just know that this O right here is oxygen. Now, what if we had a dozen waters? Okay, let's take a look at this expression right here. All right. If I had 1 dozen waters, all right, how many dozen H's would I have? Okay, well, what your mind wants to do is it wants to say, okay, well, I know a dozen is 12. And if I have 12 H2Os, right, then that means I must have 24 H's, okay? If I have 1 dozen H2Os, though, how many dozen H's do I have, right? And the answer is 2, right? For every one H2O, I get 2 H's. So for every grouping of H2Os, I get that same grouping of the part. So anything you can say about individual species, just looking at a chemical formula, right? You can also say about grouping of that species, right? And this is how we develop mole-to-mole bridges. Because if you understand that 1 dozen would be, 1 dozen H2Os would have 2 dozen H's inside it, all right? If that makes sense to you, and hopefully it does. This is 1 dozen, this is 2 dozen, 24, right? You can say the same thing about moles. Any one of these equalities, right, and let's just keep focusing on this one here, we can build what are known as mole-to-mole bridges. We can build mole-to-mole equalities, all right? If I have 1 mole of H2O, which is just a grouping like a dozen of waters, how many moles of H do I have? 2 moles of H. So now we can look at chemical formulas and we can see these mole-to-mole relationships. And why we call them bridges is because whenever we have an equality, we know that we can build conversion factors, right? We know there's 2 that we can build. Let's just show one. 2 moles of H is the same as 1 mole of H2O. So whenever I see a conversion factor now, it tells me if I have this bit of information, I can convert it, I can cancel to this bit of information, right? Using ideas from earlier in the semester, mole-to-mole bridges, right? Mole-to-mole bridges allow us to change identity, all right? Before we get to problems associated with that, and I'll probably save it for the next video, I just want to reinforce this idea and look at some complicated organic molecule. How about C2H3O4, all right? Which you don't need to know how to name. It's an organic molecule because it's made of carbons, hydrogens, and oxygens. You don't really need to know that either, okay? But it's just a good example, and you'll see these sorts of examples in Chem 101 as well, right? What are the mole-to-mole bridges we can find here, okay? And remember, if you can look at this molecule and say there's 2 C's, there's 3 H's, there's 4 O's, anything you can say about those individual species, you can make a mole-to-mole bridge with, okay? So there's a ton here that we could do. For every 1 mole of C2H3O4, how many moles of carbon do we have? 2 moles of carbon, right? For every 1 mole of C2H3O4, how many moles of H do we have? We have 3 moles of H. If I look at this one molecule, how many H's are there? 3. So if I look at a mole of that molecule, we'll have that same number of moles of H, right? For every 1 mole of C2H3O4, there's going to be 4 moles of O, all right? And then inside this molecule, we could also build bridges, all right? For every 2 moles of C inside this molecule, right, there are 4 moles of O. And for every 2 moles of C in this molecule, there are 3 moles of H. So if you can picture this molecule as being the combination of all these species together, then anything you could say about the individual species also applies to groupings of those species, and the groupings that we care about are moles. The last mole to mole bridge we can build here is 3 moles of H is equal to 4 moles of O. And I think that's it, but you can kind of see there's a wealth of information there now, where if I have information about one species, I can relate it to information about another, okay? So again, it's an essential tool that we have to sort of get down as soon as possible. I know I say that a lot, but it's really, really important. It's a foundational idea. It's a foundational tool that we'll cite again and again and again. And what we're going to do from this point in this chapter is we're going to use these tools and we're going to start applying them in different chemically relevant situations, okay? We're going to use our general conversion factor skills, but now we're going to couple these new tools to those general skills, and we're going to be able to solve some very interesting chemically relevant problems together.